All right, welcome everybody. So in today's office hour, we're going to work through any questions you guys have on the week 3 conjecture. And then if you want me to stay after and talk about any other assignments or anything like that, we can totally do that. But we're going to start off with the week 3 conjecture. So let me share my screen really quick so we're all looking at the same thing. Okay, so the week 3 conjecture, you have, oh, okay. Thanks, Anita. Will you let me know if it's not big enough as I'm writing? Thanks for that feedback. Um, okay, so in the week 3 conjecture, we're basically saying that like these lowercase letters can be any number in these rows that are defined like this. And then we want to make a conjecture about the sum of some of these numbers and products of some of these numbers and determine what row those numbers will end up in. So does anyone have a specific one they want to go over? We can start with that. D? Okay, awesome. So D, that's the one that says the product A times B is sometimes always or sometimes, and we need to determine that in row blank of table 1. So remember A is any number in row A, and B is any number in row B. So I could just choose any 2 random numbers. So maybe I'll choose like 7 and 2. And if I multiply those together, it looks like it equals 14. So it's in row B. Is that always true? Have you guys tried it out for several different numbers? Does it always end up in row B? Okay, Jody says yes. So Jody, I'll take your word on that. And also I know how these numbers work. So it should always be like if one of the products ends up in a row, it should always end up in that row. So the way that we would state our conjecture here, I'll write this over here. And Anita, let me know if this is big enough as I'm typing it. So the conjecture I would state would be that A times B will always be in row B. So that's what I want to prove.
We can't see your
Faut
screen.
la bloquer.
Oh, you can't see it
Faut
at
la
all?
bloquer, elle ne peut pas partir comme ça, les
Okay,
trucs qui j'aime pas ce genre d'enfant.
Let me share the whole screen. Let me know if this works.
C'est comme ça, ils font pour créer des problèmes aux gens là. Je ne sais pas pourquoi les enfants là sont
Is that
méchants comme
better?
ça. C'est là le mauvais.
Can you see it now?
Et quand tu t'assis là, tu l'as sorti.
Yep.
Okay. All right. Sorry about that. And thanks for letting me know. Is that big enough? I know, Anita, you were saying that you needed the writing to be bigger. Anita, is that big enough for you? Because I can
Yes,
also
that
make
works.
Okay, awesome. Okay, so this is the conjecture we want to prove. And in order to prove that, we need to have some way of describing the numbers that are in row A, B, and C. So I'm going to minimize my document for a minute, and we're just going to look at what these numbers are. So did anyone notice any specific patterns within these rows that would help us maybe algebraically describe the numbers that are in the rows? Okay, so Jody, you're noticing it adds 3. Melissa said row A is adding 3, starting with 1. So when both of you are saying you're adding 3, I'm assuming you mean like across the rows, meaning like 1 plus 3 gives you 4, 4 plus 3 gives you 7, 7 plus 3 gives you 10, and so on. Okay, perfect. Yep, and all of table 3 has that dynamic. Table 2 has a different dynamic, but we're just focusing on table 1 right now. So what we want to do is we want to see if we can use algebraic notation to describe these rows, kind of like how we describe odd numbers. or odd and even numbers, because you know how we use like 2n to represent even numbers, or 2n plus 1 to represent odd numbers. We want to do something similar, but for these specific numbers and these patterns. So does anyone have any ideas of maybe how we could represent? And in my opinion, row C is the easiest one to do. Yes. Yep. So you guys started with row A, which is great, because that's one of the harder rows. And Melissa and Amy, either one of those would work. So you could do 3n plus 1, where n is an integer, because you could have, like, if you have the integer 0, 3 times 0 plus 1 would give you the first number, sorry, in row A. And then if you do 3 times 1 plus 1, you'd get 4. And each one of these numbers could be expressed as 3 times an integer plus 1. But Amy, yours would also work just as well, because if you have the integer 1, 3 times 1 minus 2 would give you this 1. 3 times, oops, and then 3 times 2 would give you 6, minus 2 would give you 4. So either one of those would work, because they both describe this pattern of consistently adding 3. Does anybody have any questions about why that expression or both of those expressions work for row A? Okay, so the way that I would write this in my proof, so writing out my proof, I would say, because row A, or I guess I should say the numbers in row A increase by 3 starting at 1, I can express any letter or any number in row A as, and I'm going to write this as A equals. I'm going to use Melissa's, partly because Melissa, yours like kind of starts at like, you have like +1, because that's like the first one. So you can start with the integer 0. But Amy, yours would work just as well. So there's not one right way you could do either one of them, because they both represent the numbers in that row. But I'm going to use 3n plus 1. So basically, I just explained in words why this expression can represent the numbers in row A. Is everybody good with that so far?
Can you do this? Can you paint my toenails?
Okay. Gonna take silence as a good thing. So that's how we can express the letters in row A. Now the next, oh yes, yeah, I should say that it's an integer, or a whole number in this case, because we don't have anywhere they're negatives. So I should say where n is a whole number. You could also say integer as well, because the pattern in row A could continue into the negative numbers. I just didn't set it up so that it would be that way. But you could say that n needs to be an integer as well. Okay, so that would be the first part. So I've defined a algebraic way of describing the numbers in row A. And our conjecture says that anything in row A times anything in row B should be in row B. So the next thing we need to do is we need to define what the numbers in row B are in algebraic terms. So any ideas on how we could describe this pattern for row B? We mentioned earlier that the pattern is still adding 3 every time. So that should go into it in some way. Yeah, perfect. Yep, so I'm just going to actually copy and paste this thing that I said for A, and I'm gonna fix it so it applies for row B. So I'll say, because the numbers in row B increased by 3, starting at 2 this time, I can express any number in row B as B equals 3n plus 2, where n is a whole number. And I'm going to actually change this so it's an m instead of an n, because I want to show that any number in row A times any number in row B can multiply to be in row B. And if I used n in both of them, then I would have to like stick to numbers in the same column. Because like in this column, or sorry, the first column, this would be like where your whole number would be 0, because you'd have like 3 times 0 plus 1 or 3 times 0 plus 2. And like the 10 and the 11 would be where I think it would be 3. The whole number would be 3, because you'd have like 3 times 3 plus 1, which is 10, or 3 times 3 plus 2, which is 11. And I don't want to prove that it's just any two numbers like in the same column. I want it to be any two numbers. So that's why I'm using two different variables for my whole numbers. I don't know if I explained that very well. Does that idea make sense? Can you guys give me like a yes or no in the chat on that? Okay. Awesome. So this is kind of the start of my proof, because I need to algebraically describe the patterns that I'm seeing in row A and row B. And ultimately, what I want to prove is I want to prove that A times B will always be in row B. So what that means is I want to multiply, and I'll add in my words in just a second, but I want to multiply 3n plus 1 and 3m plus 2, and I want this to ultimately equal 3 times some whole number plus 2, because that's the form of the numbers that show up in row B. Does that make sense to everybody? Because like my claim that I'm making in my conjecture is if I take any number in row A, which I've expressed here, and if I take any number in row B, which I've expressed here, if I multiply those together, the result will always be in row B. And I've defined the numbers in row B to have the form of 3 times a whole number plus 2.
Just one question about that. Isn't the 3 whole plus 2 the same thing as the 3m plus 2?
So the whole number doesn't have to be the same as m. Like it might be a different whole number, which is why I didn't put it like the m in there. Because actually the only way that it would be m would be if this number was a 1. Because like if you had 1 times 3m plus 2, that would equal 3m plus 2. So if you want to, you could use like a different variable, like you could say it's going to be k, where k is a whole number. But it's going to be some combination of n's and m's and possibly other whole numbers. And so you wouldn't want to claim that it's equal to 3m plus 2. It'd be 3 times some other whole number plus 2.
So as long as it's a variable, it doesn't really matter which one.
Yeah, it doesn't matter which variable you choose, but it can't be one of these other variables you already chose. Because those, like, you don't want well, it will depend on it, but you don't want them to be the same variable. Once I get into the proof, I think you'll kind of see what I mean. So I can show you that part in just a second. But it just needs to be a whole number.
Okay, thanks.
Okay, so in my proof, I would say something like, I want to show that and I'm going to use parentheses like this, just so that like sometimes X looks like a variable to me because I teach college. So I'm just going to write it like this. It's fine if you guys write it with an X, so that's fine. So I'm going to say, I want to show that A times B will always be in row B. So I will multiply oops, I'm going to delete this part. So I will multiply these two expressions together. And you guys remember from conjecture 1 how you multiply expressions like that? Yep, you can use FOIL, that's a common name for it. You can also think of it as like double distributing. So I'd say by the distributed property, because that's technically the justification for the FOIL method. So by the distributed property, I'd say 3n plus 1 times 3m plus 2. This is going to equal what?
It's 9mn plus 3n plus 3m plus 2.
Wouldn't it be 6n?
It
Because you're
would,
going to
so,
multiply the 3 times the 2.
The 2's outside
yes.
the parentheses. Oh, it is.
Yes,
Okay,
so
I
when you,
messed it up.
which one is it? Is it 3n or sorry, 6n or 6m?
6n as in
And
Yankee.
I did it
Yep.
wrong.
No worries. I thought that you were right, so that means that I did it wrong too. So I'm glad you guys were paying attention and got that. Okay, cool. So that's the foiled out version of it. And ultimately, remember, our goal is to get this into the form where you have 3 times a whole number plus 2. So looking at this, we've already got the plus 2 part. That just kind of naturally came out of the foiling process. So is there a way that we could get this to look like 3 times the whole number? Yeah, perfect, Jody. We could factor out the 3. So that also the justification for factoring out a number is also the distributed property. So I'd say by the distributed property, oops, I can factor out a 3, which gives, we'll just copy this again. This equals 3 times, what would be the stuff inside of my parentheses? When you factor out a 3.
It would be, go ahead.
Would it be 3nm plus 2 plus m, then your parentheses, and then outside the parentheses plus 2?
Like this.
Yeah. Well,
And
plus-
then,
plus m.
Plus m.
Yeah.
yep,
Yep.
perfect. And Amy got something similar. She just arranged it in a different order, but that's basically the same thing. So this is all in the form that we want it to do. So the last thing we just need to do is justify why this is a whole number. Or an integer if you want to justify that way. So I would say by the properties of integers, well, with whole numbers too, if you add them together, it always equals a whole number. And if you multiply, the only time it doesn't work with whole numbers is subtraction, because subtraction like can create negative numbers. So we can say by the properties of whole numbers. But if you did have subtraction in your problem, like if instead of defining it as 3n plus 1, if you did, I forget who it was that did it earlier with a minus. Amy. So Amy, if you need to be able to do subtraction, I would, rather than defining m and n as being whole numbers, I would just define them as being integers, because the pattern will still work that way, and you can subtract integers. But in this case, since I only have addition, I can say by the properties of whole numbers, the 3nm plus 2n plus m will be a whole number because you can add and multiply whole numbers to get whole numbers, but maybe it's not the best way to say that, but that's the basic idea. Therefore, A times B will always be in row B. And that would be a whole proof for that one. Any questions on that? So the like process of writing your proofs is going to be very, very similar to what we did when we did even and odd numbers. The difference here is instead of having evens and odds, we have like multiples of 3. Essentially. So like we have expressions like 3m plus 2 or 3n plus 1, instead of having like odd numbers, which are 2n plus 1. But aside from that, the process is very, very similar to conjecture 1. Sure. Yeah. Okay, so maybe I'll just make some spots down here. So the rows that we've defined so far is that A, lowercase a, can equal 3n plus 1. And I'm actually just going to use n on all of these, but when you're proving your conjectures, make sure to use like 3n and 3m. But we did A equals 3n plus 1, B equals 3n plus 2. Any ideas on how we could write row C? Yeah, that one's probably one of the easiest ones. It's just multiples of 3. So Jody, you could define it the way you did. That would work. Or you could define it the way that Melissa did, because both of those accurately describe that pattern. So we could have C equals 3n. Jackie, we were working on D. So that's the one that I wrote out the whole proof for. You're working on A times B. And then someone just requested that we go through all of the rows and describe them in mathematical notation. So when we were working on our conjecture, we came up with these two, that any number in row A will be 3 times a whole number plus 1. And any number in row B will be 3 times the whole number plus 2. So that's what A and B are. And then they wanted to just go through and define the rest of the rows as well. I heard somebody's voice. Also, a couple of you guys are unmuted. Did anybody have a question, or is it just background noise?
Dr. Willis.
Yeah.
So I just wanted to ask, as far as writing these out, the way I did it, like minus versus the plus. So I based it off of the series using the variable as the position, like the first term in the sequence is 1. And so then I based it off of n would equal 1. So then I times it by 3 and then subtract 2 for that row A. So how do I think of this differently to include when you use 0? Anyway, I'm not really good with making equations for sequences, and that's where I'm having a hard time whether to do a plus one, where to do which one and how to determine if you include 0, because there isn't a position 0. And so I don't know how to do this.
Yeah, so either way works. The way you did it is not wrong. So you can do it either way. And the way that you would think about it is like you can like when you're talking about sequences, oftentimes when we're just talking about it like in casual conversation, it's easiest to say like, oh, this is the first column, so let's have this be column 1. But you could just as well say this is the 0th column because this is where I'm starting. And then the next column is column 1 because it's the first column after the 0th column. And like technically you could do that, like you could say this is going to be column -5 if you wanted to. That wouldn't be particularly useful. But it kind of depends on how you want to define your sequence. So Delaney, this kind of goes back to what you were saying. Oh, my chat just went weird. Hold on. So like you can have n represent the row or the column number that you're working on. And if you define the first column as being like the 0th column because you start there, then your expression would look like this, because you'd have 3 times 0 plus 1 gives you the number in the first row and first column. But if you define it as being the first column, you could do 3 times 1 minus 2, which still gives you the 1. So either one would work. And Amy, I think, so for your B, did yours look like this, where you had 3n minus 1?
So
Yeah,
on
good.
those, would I need to make sure that I don't have any negatives? Is that kind of where it would get into some problems? If I did that, I'd have to say I'm using integers, but then that
Mhm.
introduces, okay, I've got a whole bunch of negatives that may cause, I don't know. Is that a problem?
No, it's not a problem, because whole numbers and integers they follow all of the same rules, and integers are just an extension that allow you to take like a small whole number and subtract a bigger whole number. So integers are just kind of, the way I think about it is it like makes it more robust because it's proving it for more numbers. So I would just use, rather than saying n is a whole number, just say that it needs to be an integer, but all of these arguments would still look the same, because the properties of whole numbers, like integers, include all of those properties, and they also include the fact that you could do like 2 minus 5. Versus with whole numbers, that doesn't work, because 2 minus 5 gives you a number that's not a whole number. So Delaney, you said, can we prove that the answer would be in that row by finding what term it would be by reversing the expression? So Delaney, you can't do it for like specific examples. Well, I might not be fully understanding your question. But what you want to do is you want to show that any term or anything in the row times any other number in the other row will always be in row B. So you're not looking for a specific term number, like saying, oh, like the one in the third column times the one in the fifth column will always equal the one in the whatever number it will be. Although technically that is what this expression is. Because like if you're interpreting n and m as being the column numbers, when you multiply these together and you get this expression here, like this is essentially describing the column number. So you wouldn't want to do it for specific examples, because you want to do it for any possible number in row A and B, which is why we use the variables here. But that is what that's finding in that case. I don't know if that's what you were asking. Does that answer your question? Cool. Awesome. Yeah, and if you wanted to, you could mention that. Like if you relate these integers or whole numbers to the column numbers, you could describe that it's specifically going to be in this column of row B. And that would work. For both Delaney and Amy, would it be helpful for me to go back through this one and show how you could still, like, you could use these alternative definitions of A and B? Okay, so I'm not going to write out all the words because the words will be similar, but I'll write out in a different color what this would look like if you define them alternatively. So we'll do this in red. So instead of multiplying 3n plus 1 and 3m plus 2, I'm going to use your guys' alternate definitions of 3n minus 2 times 3n minus 1. And when we FOIL those together, oh, I should use an m here. So they're two separate integers or whole numbers. So that should give me a 9mm. Then 3n times -1 will give me -3n. -2 times 3m will give me -6m. And -2 times -1 gives me -2. So that would kind of be the parallel calculation if you defined it in the way that you guys did. And then when you factor out the 3, you would also want to do that in this case. Oh, sorry, this should be a +2, not a -2, because -2 minus 1 should be a +2. Yeah. Thanks for catching that, Leslie. So ultimately I want this to look like this, because I want it to be 3 times some whole number minus 1. And right now I don't have any minus 1 in there. I have a +2, but not a minus 1. And so this, I guess, is one place where it's a little bit harder to use your notation for it, because you would want to add in an extra step. So maybe I'll write this out here. I could say by the, what property would this be? Let me write out what I'm going to do first, and then I'll justify it. So I want to have a minus 1 in there. So in order to have a minus 1, I'm going to add 1 and then minus 1. And the justification for why I can do that is because if I add 1 and minus 1, that's essentially adding 0. And what's the name of that property that says whenever you add 0, it's still the same thing? Is that the identity property of addition, I think? Yeah, because the identity is like it's the same thing. Yeah, so we'd say by the identity property of addition, this times this would still equal this expression, which is equal, if I combine the 2 and the 1, this would be equal to having a +3 here. And so this expression is equivalent to this expression, which also makes sense because 3 minus 1 equals 2. But it's important to have it like that, because then once you get to this step where you're factoring out the 3, you want to have 3n minus 2 times 3m minus 1. This is going to equal, when we look at this expression here, we can factor out a 3, which gives us 3 times 3nm minus n minus 2m plus 1. And then outside of the parentheses with the stuff we didn't factor a 3 out of, we have this -1. So from here, we can get to here. And then you would argue, or you would explain that this is a whole number or an integer in this case, because we've got subtraction. So we'd say this is an integer. And since this whole structure matches the form of how we have defined row B to work, then therefore A times B will always be in row B. So your conclusion is still the same. The process is similar. Although I guess it is a little bit harder because you have to use this identity property to make it so you have a -1 when the foiling didn't give you a -1. So I would say it's probably easier to define them with addition, but you can still do them with subtraction if you have already started working on it anyway. Any questions on that? Yes, it's math magic. Okay, so sorry, we got a little bit derailed in that discussion, which I'm glad we did because I think that was productive. But I think what we were working on before that was we were looking through all of the rows and figuring out how we wanted to describe them. So we got through all of the rows in column or in table 1, but we didn't go through the rows in table 2. So in table 2, what is the pattern? That's happening here. Okay, perfect. Yep, so we're going to be adding 5. And I would say that row H is the easiest one to define. So let's go ahead and define that one first. How would you guys define row H? Yeah, perfect. Yep, so we'll say any number in row H can be expressed as 5 times an integer or 5 times a whole number. And then we can use that because that pattern of multiplying by 5 is describing this idea of adding 5 repeatedly, because repeated addition is multiplication. So to define these other rows, how would you guys define the other rows? You can take whatever row you want to. And you can define it either by like doing the adding way or by subtracting. The adding one will make it a little bit easier because you won't have to use the identity property in your proof, but okay, I'm going to write these down as you guys put them in. So we got G equals 5 times an integer plus 2. We got D equals, or sorry, minus 4, not minus, right? I totally said all of that wrong. Oh wait, no, G said it was plus 4, sorry. Getting all my rows mixed up. Then for row D, we have 5n minus 4. Other people described row D as 5n plus 1. So I'll write both of those in. Then we've got row E is 5n plus 2. I don't think we have F yet. And we also have some potential other definitions, because all of the ones where it's like offset by a number, you can express it either by adding stuff or subtracting. Either one would work. Yep, perfect. So we've whoever B Murphy is that for F? I think that looks right. Okay, awesome. Yeah, so it looks like we've got all of the addition definitions. So the addition ones would be kind of thinking about this as being like row 0. And I guess if you were thinking about that as row 0, you might want to think about this as 5n plus 5. Or you could just like, if you were directly tying the whole numbers to the column numbers, you would want to write this as 5n plus 5. But if you just say generically, it can be any integer or any whole number, then you can just leave it simplified as 5n, which is how I would do it. But you could technically write this as 5n plus 5 as well. Because it's still 5 times a whole number. It's just that you like took out one of the 5s essentially. And then if you wanted to do the subtraction one, for E, I believe it would be 5n minus 3. And for F, it would be 5n minus 2 and 5n minus 1. So those subtraction ones are thinking of the columns as being like column 1 and then column 2, column 3, and so on. The addition ones are thinking of it as being column 0 and so on. And as we figured out with this alternative example here, the addition ones are slightly easier because you, like the foiling will end up giving you, where was it here? Like on this one, we got the plus 2, which is the form we needed to prove that it was in row B. So the addition ones can be slightly easier, but it will work with either one of them. It just might require a little more work with the subtraction definitions. Okay, so those are the definitions of all the rows of like their structure. Are there any other conjectures you want me to go over? So we did the product of A times B. Do you guys want me to do any addition ones? Yeah. Do you guys have a preference for which one? We have like 6 of them. Okay, awesome. Yeah, we can do B. Okay, so I'll start a new proof here. So our conjecture for B is that the sum, I think we're doing B plus C, will, what do you guys think? Always, sometimes be in which row of table 1? So we're taking anything in row B, adding it to anything in row C. Okay. Yep, will always be in row B. So the sum B plus C will always. Would it be helpful if we did one that has a different form? Because the last one we did, we were trying to prove that was always in row B. So maybe let's choose one where it doesn't end up in row B, so we can do it in a different form. So maybe let's not do conjecture B. G, E, got a couple votes there. So G, we're adding 2 from the same row. And on E, we're adding 2 from different ones. So I'm going to do the different one. And what does that one equal? So we're doing D plus F. So if you take anything in row D plus anything in row F, what row does it always end up in? Okay, awesome. All right, so I'm going to state that conjecture. So we're going to say the sum D plus F, I think it was, will always be in row G. Okay, so for our proof, I'm just going to kind of copy and paste what we did at the beginning because this is just defining the variables. Or the different numbers we're working with. So I'm going to say because the numbers in row D increase by 5, starting at 1, I can express any number in row D as D equals 5 times n plus 1. And I'm going to use the addition form, but you could use the subtraction one, and it would still work, where n is a whole number. Because the numbers in row F increase by 5, starting at 3, I can express any number in row F as F equals 5 times an integer plus 3, where m is a whole number. So I'm just defining my different things. And then my goal is to show that if I do D plus F, so I'm just going to write this a little bit further down so that I can remember it. My goal is to show that D plus F will always equal what I define G to be. So maybe I should actually write it like this. So because the numbers in row G increase by 5 starting at 4, I can express any number in row G as G equals 5 times, we'll say K, where K is a whole number. Because since I want to show it's in row G, I need to define how the numbers in row G work. I'm going to make a page here so you can see it all at the same time. Okay, so ultimately, I want to show that D plus F equals 5 times a whole number plus, oh, this should be a 4, not a 3. So I want to show that it's 5 times the whole number plus 4. So I'm going to say when I add D plus F, I get D plus F equals, and D was defined as 5n plus 1. And then I'm adding that to F, which is 5m plus 1 or plus 3. So that's my equation I've got just by simply adding the two expressions together. And do you guys see any way we could simplify that to get us closer to our goal of having 5 times a whole number plus 4? When we look at the way that this is written. Yep, we could add the 1 and the 3. So I could say by combining like terms, D plus F equals 5n plus 5m plus 4. So that's good because now we've got the plus 4 part. But we don't quite have 5 times a whole number yet because we have 2 terms that are 5 times a whole number. Yep, perfect. So our next step will be by the distributed property. Because factoring is basically like applying the distributed property in reverse. I can say D, or I'll describe what I'm doing. So I will factor out the 5 in the first 2 terms, which gives D plus F equals 5 times. Will you guys let me know what should be in the parentheses?
N plus M.
Perfect. Yep. N plus M. And then our last step would be to say by the properties of whole numbers or integers. You could also use integers because they both follow the similar rules. You could say by the properties of whole numbers, N plus M is an integer, because when you add integers, you always get an integer. Or I think I was using whole numbers earlier, so, and I didn't do any subtraction, so I can use that in this case. So therefore, D plus F will always be in row G. And if you wanted to add a little bit more justification here, you could say, therefore, by the definition of row G or numbers in row G, then D plus F will always be in row G. Because the definition for numbers in row G was that it's 5 times a whole number plus 4. And so since N plus M is a whole number, that's like what K would be. Yeah. So Melissa, the always or sometimes, it will be always. So on none of these will it be sometimes. I think the only way that you could get a sometimes would be maybe if you were like adding, actually, might not. I think like if you mix these, like if you did like something in row B plus something in row F, I think it would change which rows it was in because they're not following the same pattern of going like +3 plus 5. So like the factoring step wouldn't work because they wouldn't have something in common. But for the conjectures that I had you guys prove, it will always be always. Yeah. Any other questions? So the adding one should be like pretty easy, because like the math steps are simple. Like you usually just like combine terms and then factor out a common thing. And the multiplying ones aren't terrible either. It's just a little bit more intense because you have to FOIL instead of just combining like terms. So the recordings are in the Conjecture project. So I haven't posted this one yet, but if we go to Conjecture 2, I'll show you where they are. Right here. So like here, where it says video recording of office hour for Conjecture 2, that's what it will look like once I get it posted. All right. Any other questions? Oh, Jody, I'm so glad it's getting easier. Jamie, no, I have not finished grading them yet. I meant to do that today and other things happened, so I have not finished grading them. But I don't have any of my other classes tomorrow, so I should be able to finish it all tomorrow morning. Yeah, so no worries on that. I usually try to work on them either over the weekend or on Tuesdays, but this week was a little crazy, so. I'm not sure how long it takes for the video to process. If it processes quickly, I can upload it. But I'll upload it tomorrow morning for sure. Amy, yeah, I could totally stay after and help you with that. And let you share your equation there. Before I end the recording, does anybody else have any questions? Okay, awesome. Then I will see you guys next week, and I hope you guys have a good evening. Or maybe Amy, actually, I could leave the recording on for anyone else on the recording who wants to do the subtraction way. Are you okay with that?
That's fine.
Cool. I will stop sharing my screen. I think I have to give you permission to. So you should be able to share your screen now.
I'm using two different screens, so maybe if I can, give me a second, if I can copy paste it and then bring it over.
Okay.
Or if I just email it to myself. Sorry, it's gonna take me just a second.
Yeah, that's totally fine. You also, if on your other computer you're working on, if you want to join on Zoom and share your screen on that, and then stay on the audio on
I
this one.
haven't been able to figure that out just because it's my work computer that works with Zoom, and then
Oh.
they changed something that makes it so that my home it says to update and I have to talk to somebody that's in charge. I don't know. I couldn't
All
figure
the
it out
tech
yet.
things, yeah. No, you're fine.
Yeah, so I just emailed myself the link to my
Okay.
Google Drive, and let me just see if that is something I can just share. It's not okay. Okay. Sorry, it's taking a long time to send.
No, you're fine.
I just
Um,
wanted
wha-
to make sure that my thought process was right. So, okay, I've got it now.
Okay. And
So
which
then let
conjecture
me-
were you proving? Just so I can. My
I'm
brain
just
around it
doing
when
that
you're-
first one, the
The A
A
plus.
plus B equals C. I just wanted to make sure that my thought process is right.
Mhm.
So if I share my screen, all right. So I did, I don't know if you can see this really well.
Mhm.
Do I need to zoom
Yep.
in?
Yeah, I can see it just fine.
Okay, so I went ahead and did 3n minus 2 plus 3m minus 1, because those were the two for the A and the B, and then
Yep.
it should equal 3p.
Mm-hmm. Yep.
So then when I rewrote them, so I combined the like terms and I got minus 3. So then I can factor out a 3 to give me n plus m minus 1,
Mm-hmm.
which at that point I just say it's an integer
Mm-hmm.
because you can subtract integers and still get an integer. And then that's where I stopped. So the rest of this that's as far as I got. So
Yeah.
then at that point, then I could say by definition, I have 3 times an integer, which is 3p, which is I'm done. So I had to sorry that I've got all these other things on here.
No, you're fine. Yep, that calculation series works.
Okay.
The only thing, at least from what I'm seeing here, and you might have done this further up, so if you've already done it earlier in your proof, it's fine. You just want to explain why 3n minus 1 or minus 2 is an integer. Oh, it looks like you did do that.
So where?
So I'll annotate on it. So this part right here, you just need to explain why these expressions describe row A and row B.
So does this work to do it beforehand to include with all of them? Because the numbers are increasing by 3, row A starting at 1, row B starting at 2, and row C starting at 3, we can express numbers within each sequence as follows. Do we have to do them separately?
So if you submitted this, I would give you full credit for it. And if you wanted to be like if you were describing this to someone who wasn't in our class and hadn't done the whole discussion that we had, it might not be super clear why row A starting at 1 has a -2 in it. So like, I understand why, but like, if it starts at 1, like the way I would describe it would be kind of like what you were saying earlier about how n corresponds to the column number. So you would say like in the
Okay.
first column, there's a 1. And if you do, and the
So-
columns increase by 3, that's where like the 3n comes from. But it's adjusted back. It's not just 3 times the column number, it's 3 times the column number -2, because like 3
So
times the
would you
column
say it
number.
more like this, where n is the position of the number in the series? That's what,
Yeah, you could
that's
say it
where
that
I
way.
started
Mhm.
before
Yeah,
I
you could say it
came
that
this
way.
evening. Okay, but then I would still want to say, maybe combining those two thoughts that they increase by 3,
Mhm.
where n or m or p is the position in the
Mhm.
series.
Yeah, and you could
Okay.
say like, it doesn't have to be a certain way. You can explain it however it makes sense in your head, however you think it would make the most sense to someone else if they were reading it, because that's ultimately what a proof is. It's like an essay explaining your thought process for proving whatever pattern you noticed. So the idea of, since it's increasing by 3, that's why you have the 3n, because you're like multiplying by 3 by some number. And then there's also this idea of being offset. So like in the addition ones, it's that you do like 3 times 0, and then you offset it by however much you're starting at. In yours, you're subtracting because you're thinking of it as column 1. And so you have like 3 times 1, and then you offset it however much you need to get to your starting number by subtracting.
Okay.
So
Okay.
however you want to describe that, like, I'm not going to take off points for describing it differently than how I would. But just make sure you explain where your expressions are coming from.
Okay, but meaning I need to have it be, because that's when you had said starting at 1, I thought you meant starting with the number 1, because the series does start with 1. A starts with 1, and then, is that what you meant though when you were saying
So when I was
describing it with
writing
the
it out,
addition?
yeah, when
Yeah.
I was writing it out, I was using the addition one. So with
Yeah.
that one, row A looks like this. And so in that case, since it starts at 1 and increases by 3, that's like explicitly described in that expression.
Oh, because the 1 is here, and then you,
Mhm.
okay.
Yeah, but in your
Oh,
expression,
okay.
since you have a -2, it's not as clear. Oh, it starts at 1, so therefore you -2. It's like, well, wait, where did the -2 come from?
No,
And
that makes
ultimately it
sense.
comes
Okay.
from yeah.
Okay, because when
And
you were
ultimately
explaining it,
it's because
saying
like an
starting at
offset
1,
of -2 is the
yeah.
same offset as adding 2. It's just whether you're starting at an integer of 1 or an integer of 0. Or
Okay,
column
I
number
got
0
that.
or
All right, that makes sense. Okay. Well, thank you.
you're welcome. All right. And we have a couple other people here. Do you guys have any questions you want to go over? And I can also end the recording if it's like confidential and you want to talk about your grades. But I want to keep the recording going as long as it's helpful for people.
Mine's a question about just the new one that I submitted. So
Okay.
if anybody else wants to go before me, so you can keep the recording going, that's fine.
Okay. I'm not seeing any other questions, so maybe I'll end the recording here and then we can go over that.